click the button. All right, it's 4 p.m. here in Warsaw, at least. Thank you all for joining us from all around the world to listen to another seminar at the Warsaw University Astronomical Observatory Tuesday seminar series. Today we have a privilege to host Jessie Christiansen, who works in Caltech and IPAC and NASA Exoplanet Science Institute, this complicated affiliation chain. She is a research scientist there, and she's also deputy science lead at the NASA Exoplanet Archive. And she works on exoplanet discovery, characterization, and demographics with Kepler Mission, K2, and now TESS. And we are delighted to have Jessie here to tell us about the demographics of exoplanets. Jessie, please.
Thank you, Lucas. Hi, everybody. I'm going to start off by telling you what IPAC is because nobody knows about it. IPAC is a center at Caltech, the California Institute of Technology, that administers support for a bunch of NASA missions and archives and databases. So we function as a science center for instance, for the Spitzer mission and the NASA Exoplanet Science Institute. We do data processing and archiving for a whole bunch of major projects and all-sky surveys like the NASA Extragalactic Database and the Infrared Science Archive, including a bunch of smaller missions. We also support upcoming missions. At the moment, we're supporting Euclid, Roman, Spherex, NEOCF, Surveyor, and Ariel Case. We have an amazing crew of people who do media outreach and education as part of IPAC, and it's just a really great place to work. So that's what IPAC is if it ever comes on your radar. Okay, but today's talk is about exoplanets. You've had this whole series of talks so far. I'm going to help, I think we're getting towards the end of the seminar series. I'm going to help try and kind of add some of these pieces together so we get a picture of the bigger puzzle. So this is the distribution of known exoplanets before 2010. So we have period on the x-axis and size on the y-axis. So Earth is out here at 1 times the size of the Earth, 365 days. These are the inner solar system planets, and these are the known planets pre-2010. So you can see they're very, very different from the inner solar system planets. They're much closer to the star than our planets. So these are orbiting their star in just a few days, and they're much larger. So these are up here at Jupiter size. Jupiter's about 11 times the size of Earth. So these are the hot Jupiters, this new class of planets we found. Today, the picture looks a lot more like this. We've managed to really fill in this space between the hot Jupiters and the inner solar system planets with thousands and thousands of planets. And I'll tell you a little bit how we did that. But the exciting thing is now that we have this huge number of planets, we can stop stamp collecting and start asking some real science questions. So what is the underlying population? What's the true underlying population of planets? How do stars affect the planets they form? You know, do big stars make big planets and little stars make little planets, metal-rich stars, young stars, old stars, active stars, binary stars? How does planet occurrence change as a function of stellar properties? And core to that, underlying that, what are the physics that drive planet formation? If big stars make big planets, why? You know, what's different about their disks? Is it something to do with the mass in the disk or the surface area of the disk? Like, what is the actual physics that's happening? So this is exciting for me, so we can stop, you know, talking about, oh, they found the next biggest planet, and start being like, okay, they found a whole class of planets that occurs this often. So just as an overview of today's talk, I'm going to talk about Kepler a lot because that's where I've spent the last, 11 years of my life working. And on K2, Kepler's sequel, I'll talk a little bit about TESS, which is the current NASA mission that's finding planets. And finally, I want to step back and take more of a 30,000-foot view and say, like, where are we at with understanding these underlying physics, and how can we move further? So Kepler was a NASA mission that launched in 2009. It's a 1-meter optical telescope. So this whole thing here is like the size of a small school bus. It's not too big. It uses the transit method. So I know you've heard about a bunch of different methods at this point. So just as a refresher, the transit method is the one where when the planets are lined up just right, they pass in front of the star and block some of the light. So you don't actually see this top thing, that's an animation. What you measure is the brightness of the star over and over again. This is 500 hours of Spitzer data on TRAPPIST-1. And what you do is you look for these dips. And as a planet goes in front of the star, it blocks some of the light. So you get a lot of information from transits, even just measuring the brightness of a star over and over again. You get the number of planets that are lined up this way. You get the periods of those planets, which is the distance between the dips. You get the sizes of the planets, which is the depth of the dips. You can see little planets make little dips and big planets make big dips. So you actually can get a lot of information just from measuring the brightness of the star over and over again. The main science goal of Kepler was to measure how common planets like the Earth are. We call it A to Earth. So what fraction of stars like the Sun have a rocky planet like the Earth in the habitable zone? Those were the 3 criteria we used. Sun-like stars, a rocky planet, not like an ice giant or a gas giant, a rocky planet in the habitable zone. And to do this, we monitored a patch of sky about 10 degrees by 10 degrees for 4 years, and we measured the brightness over and over again of 200,000 stars in that patch of sky. You know, as I said, these have to be lined up just right in order for these to transit. Most planets don't transit their star from our point of view. So that's why we had to look at so many stars just for the statistics. Okay, this is the only slide that has an equation on it. So don't just go and start reading your email. It's very straightforward. We'll get through it. The fraction of stars that have a planet like the Earth in the habitable zone is really easy. It's the number of real Earth-like planets you found in your sample, accounting for things like false positives. You know, sometimes you might call something an Earth-like planet. It turns out it's not. Divided by the number of stars around which you could have expected to find Earth-like planets. And this accounts for things like how noisy that star is and the geometric probability that you were lined up just right. So if you found 10 stars, 10 planets like the Earth, and there were only 100 stars around which you could have expected to find them in your survey, your A to Earth is 10%. We've got it. So yes, the number of stars is a function of the geometric probability of transit, and the probability is a function of the signal to noise that you actually saw it. This little P here, this is what I spent the last 11 years measuring for Kepler, but we finally have it. So how do we measure A to Earth? We need a stellar sample where we understand the stars really well and hopefully really uniformly. What we don't want to do is like add parameters from different surveys together because there might be offsets or calibration differences between the 2 surveys. We want a uniformly produced stellar sample. We want a uniformly produced set of planets, hopefully completely or algorithmically derived. If humans are in there vetting the planets and saying this dip looks good and this dip looks bad, that's really hard to quantify. And that's partly why this big P took so long, is because we had to come up with a way to automatically generate a planet candidate catalog. And finally, we needed to understand these 2 effects, false positives. So that's the number of things you called Earth-like planets that weren't Earth-like planets, and how complete your survey was, or false negatives. So how many times did you miss a planet that you would have expected to see given its signal to noise and the geometric probability of transiting? Okay, so that's A to Earth. And now I'm going to just pull the rug straight out from under your feet and say that in the literature, what we've actually been comparing is something called gamma Earth, which is however you decide to fit your population. A lot of people have different ways of deciding how they're going to fit a occurrence rate. So some people do it in grids. So they like choose a period and radius of the planet and they say, in this bin, the occurrence rate is XYZ. Or some people fit like functions as a function of period and radius, and they try to fit the whole population at once with a power law and say, okay, across this space, the power law looks like this. So gamma Earth is a way of trying to equalize all of that and just say, however you did it, just tell me what your prediction is at the value of Earth, 1 Earth radius and 1 Earth period. So that means it doesn't matter if you fit a grid, doesn't matter if you fit a model, a function, just tell me what the value is at gamma at the period and radius of Earth. Okay, so where are we at with calculating A to Earth? We have our final planet candidate catalog, very exciting, came out a few years ago now. And in that catalog, this is the distribution of those candidates. We have measured the completeness and reliability finally, yay. So we've got ingredients, we've got ingredient 2 and 3. With Gaia DR2, we finally have a fully updated, uniformly derived set of parameters for the stars in the Kepler field, those 200,000 stars. So that's ingredient 1, hooray. And we have a better understanding of this new completeness loss that we were seeing. It turns out when we were measuring completeness, so how well we were doing at recovering signals, I was assuming that all of the signals in a given light curve were independently recoverable of each other. So it didn't matter if you had multiple signals in the same light curve, you could calculate the probability of discovering each one independently. It turns out that was a bad assumption because the pipeline, when we're searching for signals, actually penalizes subsequent detections in the same light curve. So this blue curve here shows, as a function of the signal to noise, measures our measure of signal to noise, how easy it is to recover a given single planet, the first planet in a system. And this is the fraction of time that gets detected. So up here at quite high signal to noise, you can see we're plateauing at maybe 90-95% of the time we're going to detect this. For subsequent planets in the same light curve, so now this is if you have 2 or more planets, your ability to recover them is actually degraded significantly by the pipeline. It's down here at more like 50%. So this is a new wrinkle in the detectability of planets that most of us haven't taken account of in our calculations yet, because we've only just really discovered it. And this was work that I did with a student, John Zink, and there's John. Okay, so where are we at? This is the first half of the last decade's attempts to measure gamma Earth. And the reason I show this is because this is 3 orders of magnitude in gamma Earth, and you can see this huge spread. And this was before we had the Uniform Planet Catalogue or the Stellar Parameter Catalogue or the completeness and reliability. So people were doing a lot of guessing here about what those things might be. So this kind of accounts for this huge spread. Now, in the last half of the decade, in particular in the last 3 or 4 years, you can see that we've converged down somewhat. Now that we have this final catalogue and we have stellar parameters and we have completeness and reliability, now a lot of these things here are a lot of the difference here is likely due to methodology, but we're not sure. So one of the things I'd really like to do is a community Kepler data challenge where we all make the same set of assumptions about the planet catalog and the stellar parameters and reliability and completeness, and see if everybody's methodology is what's creating this continued spread. You can see even in the last few years, we kind of go between 10 and 50%. That's still a pretty exciting statement to be able to make. Between 10 and 50% of stars like the sun in the Milky Way galaxy, and there's billions of them, have a rocky planet in the habitable zone. That's pretty wild. These uncertainties are still pretty big, and that's largely because of the small numbers. We actually didn't end up with many candidates at that period and radius range. So there's a lot of extrapolation happening, which I'm going to talk about in a second. Okay, how do we improve this? One of the things we haven't taken full account of yet is the multiplicity of the stars we're looking at. So we assumed that most of these stars were single, just based on their colors, but that's not a great assumption. We already know that's not a great assumption. And the problem is if you assume the stars are single, you get 2 things wrong. One is that, I mentioned the size of the planet from the size of the dip. That's only true if you know the size of the star, because it's a fractional dip. The planet is covering some fraction of the star's surface. It's a relative amount. So if you don't actually know the size of the star, if that total flux that you're counting comes from 2 stars or 3 stars, then you're going to get the radius of the planet wrong because you've got the radius of the star wrong. And for the non-host stars, for the stars that you didn't find planets around, where you were measuring how complete you were saying, well, we would have found an Earth-like planet around that if there was one, then you can't say that because you thought it was a single planet and the dip would have needed to be this big, but actually it's multiple stars, and the dip would have needed to be much bigger in order for you to be able to see it, because the light gets diluted from all of the stars in your photometric aperture. So what we're doing to try and address this is I'm leading this little pilot study at Palomar Observatory, where we selected 200 of the roughly 2,000 single stars that we think we should be sensitive to Earth-like planets around. And we're just doing a blind, basically, survey of those stars. Are they single or not? So this is using high-resolution adaptive optics imaging from the ground, and we're trying to measure, you just look at them and say, hey, is it single or not? This was the very first one we looked at of those 200, and it was a triple star. So immediately I was like, oh, I'm so glad we're doing this. And the goal is to have this measurement soon. Unfortunately, because of the pandemic, we didn't actually get to complete our sample yet. They obviously had to take the telescopes offline for a while. So we're about 2/3 of the way through. The preliminary result from just the initial set of data is that the multiplicity of the stars might be higher for non-host stars than host stars. And we know that binarity of stars suppresses planet formation at some distances from that binary. It depends on the configuration of the binary and where there are stable planetary orbits. So that maybe not too surprising, but again, something that hasn't been corrected for in those 200,000 stars. This is the extrapolation I was talking about. So here are the candidates for Kepler. And you can see this is this is out here, 365 days, 1 Earth radius. There's not a lot of candidates out here. We don't think that's because they're rare, but because this is exactly where the Kepler's detection sensitivity falls off. You kind of have like these contours here of how sensitive we are. So we needed to correct for this and say, okay, we missed most of them. So when you're making a big correction, that's already a bit worrying. But a lot of what we do, there's lots of candidates that are bigger and at smaller periods. And there are physical reasons. You might assume that, there's a mass function or a radius function from the star. So people try and extrapolate from smaller periods to longer periods and from bigger planets down to smaller planets. The problem is, if you extrapolate from this box here out to here, you're assuming that the same formation mechanism created these planets as would have created these planets. But we know that's not true. There are rocky planets here that are actually, we believe, they didn't start as rocky planets. They started as bigger planets, like Neptune-sized planets, that were stripped down to Earth-sized cores because of their proximity to the star. I mean, remember, these are very short periods. This is like 50 to 100 days. So these short period things, and even shorter, there's like a whole bunch below 50. These short period things, we can't assume that they have the same origin as the long period things because some of them are stripped cores of larger planets. So there's a two population component at short periods. And there's this paper by Ilaria Pascucci where she showed that depending on exactly the period range over which you extrapolate, starting from 2 days going up to 25 days, it changes your gamma Earth by a factor of nearly 10, by a factor of 4 to 8, just where you anchor this. And that's because there's so many short period planets that they have a lot of power when you're fitting this function. If you have wiggle room, none of it's down here, it's all up here. So it's kind of the tail wagging the dog sort of thing. So depending on where you cut this, gamma Earth drops way down if you cut out all these short period things, because they're giving you a false sense of hope. There's this huge number of planets at short periods, and you're like, wow, that means there must be heaps of planets at long periods. But actually, you won't have that second component of the Neptunes that have been stripped down at these long periods because there isn't the radiation. So this is a bit scary and something we haven't really taken into account yet. Okay, so with Kepler, moving forward, we've got to do these stellar and planet multiplicity corrections that I mentioned. We'd like to do a better job with our reliability. We do have a number of fairly unreliable candidates out near the Earth parameters. We say unreliable because they're not very much above the noise, which is always worrying. But we could potentially go back and just look for more transits. Unfortunately, Kepler broke, so we can't do it with Kepler, but something like Hubble, for instance, you could go and see more transits of these planet candidates and prove that they are really planets. And then, referring to this very last thing that I mentioned, improve this population model to account for the fact that there's two populations at short periods. But of course, what we really need is more data. So tick that off your bingo card if you have it. Earthfinder is a radial velocity concept for a space-based radial velocity mission. It's another way to find planets. Roman, I know you had Scott Gowdy come give a talk last month about Roman, so you've heard all about that, but that should be sensitive to Earth-sized planets in sunlight, in habitable zones of sunlight stars. Plato is a European mission. I'm not sure if Poland is a part of that. I should have checked, but there's a Plato mission that will go back and do a whole bunch of photometry of the sky, including the Kepler field. So that might actually be able to recover some of these candidates in the same way that Hubble might have. And finally, there's a Chinese mission concept under study, Earth 2.0, which will basically be a replica of Kepler and go back to the Kepler field and look again. So Kepler does have candidates. We just haven't, they're all a bit, you wouldn't get in a spaceship and go there. They're not that reliable. Okay. As I mentioned, Kepler broke, which was a huge bummer. But we were able to recover a second mission out of the spacecraft. It wasn't able to point out of the ecliptic into the field that it was originally looking at anymore because of the way it broke, but it was able to point in the ecliptic. So we spent 4 years doing an ecliptic plane survey. Here's the fields around the ecliptic. And each field we could look at for 70 to 80 days. Each field had 10 to 30,000 stars in it, depending on the density. You can see some of the fields are quite close to the galactic plane and some of them are quite far away. The exciting thing about K2 was where Kepler was, very statistically driven. Here's our one question we need to answer. Most of those 200,000 stars were FGK, field stars in order to answer this question about Earth. The target list for K2 was entirely guest observer driven. There wasn't any underlying core driving science anymore. So it was basically just like, hey, here are the stars that we'll look at. Which ones are interesting and why? So we got to basically drive the target list from the community. What that means is that many different kinds of stars were observed, so including stars spanning a much wider range in stellar metallicity, in stellar age, and stellar type than Kepler. And that really lets us start asking some of these much more interesting demographic questions. Like you start from Earth around a sun-like star, but then you say, how does it change with stellar metallicity? How does it change with stellar type? So we've started looking at this now. So this plot shows from the Kepler data how the occurrence rate of small planets, 0.5 to 2.5 times the size of the Earth, in short periods, less than 10 days, changed as a function of stellar type. So remember I said the Kepler sample was mostly focused on FGK stars. So you can see already there's hints that as a function of spectral type, smaller stars seem to be making more small planets. So that's already interesting because it's a little counterintuitive. You think bigger stars have got more mass in their protoplanetary disks. They might be able to make more planets. But it turns out, at least for the small planets, smaller stars are better at making small planets. And you can see all this daylight that I've left here above the M dwarfs. I'm kind of telegraphing the answer a bit. For the M dwarfs, there were only 3,000 studied by Kepler out of those 200,000. You've already got this result here for the early Ms. This kind of keeps rocketing up as a function of stellar type. So the M dwarfs have a much higher rate of these small, short period rocky planets. Potentially rocky planets. 2.5 times the size of the Earth. It's getting big. If you just look at the mid Ms, so this is like M3, M4, M5, you get a very large uncertainty because there's only one detection of a planet in this range around an M dwarf. So you're doing a lot of correcting here. But you can see even within the mid Ms, this rise continues, M3, M4, M5. Actually, I think it was the M5 bin that just had one. So with K2, which was again the sequel to Kepler, that we've looked at 30,000 M dwarfs. So we've increased the sample by a factor of 10. So we're going to try and get these uncertainties down and to say, like, what is the form of this function? Like, is it really exponentially rising? And if so, it has to turn over somewhere. Otherwise, every brown dwarf you see would have a full family of rocky planets around it. So how does it keep increasing and where does it turn over? That's what we want to ask with K2. And this is work being done by my postdoc, Kevin Hardegree-Allman. Okay, stellar age. So this is a cartoon showing, as a function of time, some of the different processes that have been proposed to explain planet formation and planet migration. So very quickly, there's a few different ways planets likely form. One is by gas accretion. There's just like a runaway gas at the start when the disk of material is still there, and the planet, grows very rapidly and gets this big gas envelope around it. So that has to happen very quickly while the protoplanetary disk is still there and all of that gas is available. So that's in the first, 10, 20 million years. Another potential way planets grow likely is growth by collision. So this is, pebbles stick together and form planetesimals. Planetesimals stick together and form planets. That takes a long time. That's, that's the early stage of what we think our solar system was like, and takes more like 100 million years while these things are all kind of slowly growing and accreting. Then there's different ways that planets migrate. For instance, the hot Jupiters, we don't think necessarily started where we see them. They clearly started somewhere else and moved. What pushed the planets to where we see them today? One is potentially disk-driven migration. So while the disk of material is still there, it's providing a torque on the planets. They're losing energy to the disk. It's like they're trying to go through molasses. It's very difficult. So they lose energy. and they migrate through the disk. But that can only happen while the disk is there. So again, only this first like 10, 20 million years. Or there's migration due to planet-planet scattering, which is where the planets exchange energy over very long time scales with eccentricity and impact, their inclination basically changing. And so we think, for instance, this might have happened in our solar system, like Jupiter and Saturn may have swapped places. We may have kicked a giant planet out of the system. There may have been 5. So this takes a lot longer though. This just keeps going basically until the system is dynamically cool and not really interacting anymore. So you can see these different proposed mechanisms have very different timescales associated with them. So if we could measure planet occurrence rates as a function of time, we might be able to say, okay, at these very early times, we already see hot Jupiters. Therefore, they must have grown very quickly and moved very quickly while the gas was still there. Or, for instance, if we look here at the Hyades and Praesepe at 600 million years and we still don't see hot Jupiters, then, okay, maybe they didn't grow very quickly and migrate very quickly. It's a slow process. So these young clusters here that I've written in red, Upper Scorpius, Pleiades, Hyades, and Praesepe, they're all young clusters that were observed by K2. So one of the things we're trying to do is, as a function of age, map out this occurrence rate. And this is work that I'm doing with Josh Schlieder and the California Planet Search team. Okay, so let's go back to those 3 ingredients. Stellar parameters. We have produced a uniform stellar parameter catalog. We did this by using Gaia DR2 and LaMost. LaMost had spectra for 27,000 stars, and Gaia DR2 obviously gave us distances and parallaxes and proper motions. So we've derived a very good set of stellar parameters for those 27,000. And then we used that set as a random forest for training our machine learning algorithm on the rest of the stars that didn't have LaMost spectra, but they did have Gaia DR2 and photometric colors. So now we have a full set of 185,000 uniformly derived stellar parameters for our A, F, G, K, M stars, including temperature, log G, and metallicity, and mass and radius. Here's what it looks like when you try to derive these just using photometry without the LaMost training set. And in particular, what I want to show you is all this contamination down here by what turn out to be giants. Giants and dwarfs are the same color, but what you get from Gaia is these distances, so you can differentiate between those populations. So this is what it looks like when it's all cleaned up. And again, this is work led by Kevin. One exciting thing, when you have good stellar parameters, you get better planet parameters. So with this very good stellar parameter catalog, we were able to rederive the planet parameters for the existing K2 candidates that had been found by the community and rediscover this Kepler, this really interesting Kepler result, which is that the radius distribution of small planets is bimodal. So this is planet radius. So this 4 Earth radius is Neptune. 1 Earth radius is Earth. And before this was discovered, you might have expected some kind of smooth function as a function of radius with the occurrence rate of planets. But what we see for short period small planets is this bimodal distribution. Nature seems to be really good at making sub-Neptunes and really good at making Earths, but not really good at making and keeping 2 Earth radius planets compared to either side. So what we found with K2, which is this blue curve, is that in a completely different patch of sky, this is still true. So it's not some weird quirk of the Kepler data, but it's a fundamental property of short period small planets that they have this bimodal distribution. So that's really interesting and leads to lots of questions about, what's sculpting this valley and when does it appear and how does it change as a function of teletype, all those interesting things. Okay. Our second ingredient is a planet catalog. So this is work that John's been leading. We've just finished it. We have 780 planet candidates, including 245 that are new. We have measured our completeness. There's our completeness curves, and our reliability. There's our reliability. So we have the third ingredient as well. So next step, occurrence rates. We're circulating the draft paper around the co-authors right now. It's very exciting. So that catalog will be out soon. Keep your eyes out for it. Okay. That's where we're at with K2 occurrence rates. So let's move on to TESS. So TESS is a currently operating NASA mission launched just over 3 years ago, where Kepler was a single 1 meter telescope. TESS is 4 10 centimeter telescopes. So they're actually pretty small. They're just like off the shelf 10 centimeter lenses. But it's a very, very wide field of view. So what this animation is showing is that in one TESS image, you get 90 degrees of the sky in a swath that's about 24 degrees wide. So the way TESS is working is it had a 2-year prime mission. It spent 1 year tiling out the southern hemisphere, and then the second year tiling out the northern hemisphere. Now we're in our 3rd year, which is the extended mission. So we're going back to some of the places we've done before. We're now going to the ecliptic, which we avoided before, which was obviously where I was just showing you K2 did its survey. So I'm really excited that TESS is going to recover and help us confirm a bunch of K2 candidates. And because it's doing the whole sky, it's predicted to have a very large planet yield. So that plot that I showed you at the start with, and here's today, that's 4,000 planets. So TESS is predicted to yield something like 16,000 planets in total, so quintupling our current number, which is obviously, from a demographics point of view, going to be very interesting. However, TESS is not a statistics mission. So I've been, because I'm coming in with my Kepler demographics hat on, I've been encouraging the science team to make decisions where they can to make, the TESS sample as statistical as possible. And every time I get told TESS is not a statistics mission. TESS's goal is to measure them, is to find planets smaller than Neptune that they can measure the masses of. The problem with the Kepler targets is they're all quite far away. It's a 1 meter telescope that went kind of deep in one patch of sky. So most of the Kepler candidates, of those thousands and thousands of Kepler planets and candidates, they're too faint to really do anything with. You can't really measure radial velocities. They're around 14th, 15th, 16th magnitude stars. You can't get atmospheres. They're good for a statistical sample, but on an individual planet by planet basis, there's not much you can do with them. So TESS's goal is to look at the whole sky, all the bright planets, and find the ones that are nearby and bright that we can do all these lovely mass and atmosphere composition measurements with. But TESS is looking at the whole sky every 30 minutes, which is the same cadence at Kepler, or that swath of the whole sky every 30 minutes, and is doing the entire sky over the course of its mission. So there's still scope for doing really interesting statistics if we decide to do it that way, which requires money, obviously. Partly I'm excited because the TESS sample is so close and we can get masses. Now we can start to ask questions about classes of planets. So instead of just being like Neptune-sized planets occur 10% of the time and Earth-sized planets occur 50% of the time, we can say, do water-rich planets occur more often than rocky planets? Do iron-rich planets occur more often? How does that change as a function of, for instance, the iron abundance in the star? Are they correlated? And really start to work out like the demographics of classes of planets. I think that's really interesting. And as we start to be able to get these larger and larger samples of planets where we can measure atmospheres, we might be able to start to explore these trends like this. This is atmospheric metallicity as a function of planetary mass. Big planets appear to have fewer metals in their atmosphere than small planets. This was a trend we had seen in our solar system, and now we're trying to put exoplanets on this plot, and you can see there's not much of a trend yet. But when we have a much larger sample from TESS, we can actually start to look at these trends in atmospheric composition. And we can start to say, are cloudy planets more common than clear planets? Are hazy planets more common than clear planets? This is all really important for things like Ariel, which is an ESI mission launching later in the decade, which will be doing large-scale surveys of exoplanets, of their atmospheres. Really, with TESS, the major constraint is following up all of these planets. There's thousands of candidates already. We just published a paper with 2,200 candidates. The problem is they all need, lovely big telescope time to follow them up, and we don't have 2,000 big telescopes sitting around waiting to do it. There is a TESS demographics working group, so if you were interested in any of these TESS demographics questions, get in touch. I'm the chair of that group. Okay, great. In the last 10 minutes, I want to step back. We've talked a lot about transiting planets so far, which obviously I think are very interesting, but are actually confined to a pretty small area of solar systems. We haven't explored very far with transits. And that's because transiting planets are sensitive to the shortest period planets, because you've got to wait for these transits to happen. So if you have something that has a period of 40 years, you probably haven't seen it transit yet, given that transiting surveys have only been happening for a decade or two. So here is the parameter space that's populated by transiting planets. So now I've switched it slightly. this axis is now semi-major axis, the distance between the planet and the star, and the y-axis is now planet mass, or m sin I. So here's what's probed by transits. This is what's been probed so far by radial velocity surveys. So you can see in semi-major axis, we've moved out about an order of magnitude because radial velocity surveys, frankly, have been going for longer than transiting surveys. But you can still see, we're confined to within about 10 AU and really only sensitive to the largest planets so far. We don't think this absence of planets down here is real. It's very much a function of the fact that RV detection surveys the sensitivity drops off right here, which is where you see this under envelope of planets. Here's the microlensing distribution. You don't see as much of a trend with size because microlensing, as I'm sure Scott told you, isn't sensitive to the mass of the planet. It's sensitive to the mass ratio between the planet and the star. That's the observable that you see in the microlensing light curves. And finally, out here at the furthest distances, you have the directly imaged planets, and they have the opposite sensitivity to transit and radial velocity. The further away the star is from the planet, the easier it is to see because, direct imaging is where you're trying to block out the light for the planet and search around block out the light from the star and search around for the planets. So the further away the planet is from the star, the more easily you can differentiate it from the star or like a little speckle around the star. So it has the opposite sense from the others. But if you put it all together, you can see we've actually explored 5 orders of magnitude in semi-major axis and 5 orders of magnitude in planet mass. So there's a lot of opportunity here. Even though each technique is only sensitive to its own bit of parameter space, and each technique has produced occurrence rates in its own set of parameter space, there is overlap, right? The transits and the radial velocity overlap with each other. The radial velocity and the microlensing overlap with each other. Radial velocity and microlensing and imaging all kind of overlap out here at giant planets. So there's opportunity here to see if they agree and to even improve our estimates by being able to fit things over larger distances. There are problems though. In order to get all of these different techniques on the same plot, I've had to do a bit of juggling, a bit of sleight of hand. I don't know if you've noticed. So for instance, transiting planets, you're only sensitive to the radius. This is the size of the dip, gives you the radius of the planet. So I've had to make some assumption about the mass-radius relation of planets to transform from radius to mass. And there are different estimates in the literature, different types of relations that have been measured and estimated. So you might already disagree with my choice that I made here to switch from radius to mass. Radial velocity gives you a minimum mass. It just gives you the mass of the orbital motion projected along the line of sight to you. So we know that all of these blue points are effectively lower limits. And you can kind of normalize over what your expected distribution is to kind of get a population out, but all of these points on this plot are minimum masses. Microlensing, as I said, doesn't give you the mass. It gives you the mass ratio, and it gives you the projected separation. So that's 2 axes that we've had to make assumptions over. And again, you can integrate over the expected stellar population to get some average type of planet out of it. But you've had to do that to get this on this plot, to get a mass out of a mass ratio. And finally, with direct imaging, you're actually measuring the brightness of this little speck on the sky in a certain waveband, and then using models to turn that back into a mass. Like you have to make assumption about the age and say, then you've got like hot start and cold start models and say, okay, this is the mass of an object that would be this bright at this wavelength at this age. So you can see I've had to do a lot of work just to get these on the same footing, which is not necessarily great. In fact, none of these techniques on their own gives you the mass of the planet. You need multiple techniques and multiple assumptions about the star in order to get a mass. But that doesn't mean we've completely broken it. I was able to get here by making some assumptions. The other thing that's kind of hidden in this lovely 2D plot that I made is that there's this whole third axis of stellar type and stellar properties. I've just kind of collapsed it all onto this plot agnostically, like, yay, look at all these planets. They all hang out together. The problem is each of the different techniques is sensitive to different stars as well. So transits so far are dominated by F, G, K, and M field stars, and that's largely because of Kepler and K2. And those are at, on average, 1,000 parsecs. Radial velocity is very much dominated by close, inactive FGKM stars, so quiet stars. Radial velocity surveys, if your star is very active or rotating very fast, then you won't be able to disentangle the planetary signal from the stellar signal, so they throw it away. But that's an important bias, because if quiet stars have different types of planets around them for various reasons, like people think that planet radius valley I spoke about might be sculpted by stellar activity, stellar radiation. If there's a bias between the types of stars between transit and radial velocity, then the planet populations detected by those techniques may be different. And that's the kind of selection effect I'm trying to get at here. So where radial velocity is nearby stars, microlensing is the most distant stars. So microlensing surveys look towards the bulge, which is the center of the galaxy, which is like 30,000 light years away, and find intervening stars. So some of them may be nearby, but on average, they're tens of thousands of light years away. So if there is some, for instance, function of planet occurrence as a function of the galactic radii, like maybe it's very difficult to make planets very close to the center of the galaxy, and that falls off as a function of distance, then the planet population that the radial velocity is looking at is different from the planet population that microlensing is looking at. And finally, direct imaging is sensitive to the nearby young stars. So the reason direct imaging is sensitive to young stars is because we're basically looking at the residual heat from the planet formation. So these planets, we're looking for the planet's own light, right? We block out the light from the star and we're looking to see planets around them in their own light. And planets emit the most radiation when they're young, and they're still, all of these asteroids and comets and crashing together and planetesimals, and that all lets off a lot of heat. So all of this residual heat from formation is still radiating away. But maybe, as I said, because of these different migration and formation mechanisms, maybe the population of planets around young stars is different from the population of planets around old stars. So now I've hopefully completely terrified you about the prospects of doing this. But all hope is not lost, because there are still overlaps. You can still find parts of space where you could do this, which means that I think it's possible that we could build this planet demographics ladder, analogous to the cosmological distance ladder with, supernovae and standard candles and Cepheids, where people measure distances and then calibrate them together in the overlap. I think we can do the same thing with planets. We could get a census of the entire solar systems, from the very closest planets to the very most distant planets, around many, many different kinds of stars, if we can put these techniques together in a careful, thoughtful way. And there have been some attempts to do that so far. So this is a paper by Christian Clanton and Scott Gowdy, showing a combination of radial velocity and microlensing over, so here's period, and then here's M sin I. Most of this space is upper or lower limits, but they were actually able to show, that there's some peak in the planet occurrence rate between, 1,000 days and 10,000 days. So out between like 3 and 10 astronomical units, that there's some peak in the planets. So each of these rows kind of has its brightest value around this range from 1,000 days to 10,000 days. So this is actually borne out by, this is a paper from Eric Nielsen showing a bunch of imaging survey results out past 10 AU. So he was adding this new GPIs result to some previous limits and trends from Brendan Bowler and earlier papers. These two lines here are radial velocity results. So this was a long-standing radial velocity trend from Cumming et al. In 2008. And this was a new result from Rachel Fernandez in 2018, where she took the Mayor 2011 catalogue of radial velocities and turned it into an occurrence rate. Now, for a long time, if you imagine without this red line, for a long time, we knew that the white line, this radial velocity trend from Cumming et al., couldn't keep going, because out here at 100 AU and 1,000 AU, direct imaging would have just seen scads and scads of planets, and they weren't. They were seeing very few. So we knew that this had to turn over at some point. So these two new results from radial velocity and direct imaging show this same thing that this combination of microlensing and radial velocity was showing, is that there is some turnover between 1 and 10 AU. So we disagree exactly where it is, obviously, between if we do this independently. So the goal is that we do it simultaneously, that we measure the occurrence rate of radial velocity and imaging planets together and see if we can find this turnover. Because if you do it piecemeal with these different stars and these different sets of parameter space, you end up with these bias offsets between them, and the methods don't quite meet, and you're like, oh, okay, well, we're really close, but we're not there yet. So my goal is that we do a lot of this simultaneously with across the multiple techniques. Okay, great. So I'm going to finish by saying you did see this talk by Scott last month showing where Roman is sensitive, and I've just overplotted that here, and you can actually see, like, for the giant planets, Roman actually crosses all 4 of the sensitivity regions, so transits, radial velocity, microlensing, and imaging. So Roman may be able to really help us secure these different detection techniques onto a single playing field. So I'm really excited about the prospects of Roman with helping with this exercise. So I'll just put up my summary and say, things are moving forward with Kepler. We're getting close to Gamma Earth. We're really close to being able to do fun, exciting occurrence rates with K2. We're not there yet with TESS, but I'm excited about the prospects, and hopefully we will be there soon. And in the big picture, I'm really excited about, we're really close to being able to start answering really serious questions about planet formation migration across the entirety of solar system space in terms of distance, in terms of period, in terms of mass, and in terms of stars. So I think the next decade is going to be super fruitful in terms of really unveiling the entire picture of solar systems. Thank you.
Excellent. Thank you very much. I'll do the clapping on behalf of everyone. Thank you for this excellent talk. Question time. People on Zoom here, if you have a question, please raise your Zoom hand so that I can see you, and then you'll be able to ask your question. Before people come up with questions, I would just wanted to comment about the Plato. We are aware of this mission, but we're not involved as a country. I know people who are involved, but at least not in Poland. Maybe I'm not aware of some. And there is a question from Przemek, please.
Hi. What are typical distances to stars detected, to planets detected by Kepler? And because you said they're relatively far, but we cannot really detect transit planets like in the galactic bulge. So what are distances, and how properties of exoplanets might depend on the distance from?
Yes. So I don't have it in the backup slides. So the average, the bulk of the Kepler stars are between 1,000 and 3,000 parsecs. So that's like between 3,000 and 10,000 light years. There are, a few hundred that are closer than 1,000 parsecs, but the bulk of them are far enough away. Now, if you think about the fact that, that's about a third of the way between us and the center of the Milky Way. So we've done like a cone kind of out of the Milky Way. We didn't look in the galactic plane. We looked sort of out of the galactic plane. So we've done like a cone sort of along one of the arms. We didn't look towards the galactic center either because it'd be too crowded for transiting planets. It's hard to work out what the host star is. So that's kind of the, like, in 3D space, that's kind of the space we looked at, a cone coming out of the plane, about a third of the length of the distance between us and the center of the galaxy. So with Kepler, we're not really expecting to see distances with changes in planet occurrence rates within Kepler, because we're not really looking in or out of the galactic plane. Now, as for why there might be planet occurrence rate differences as a function of galactocentric distance, for instance, there's things like, bulk metallicity gradients along that. There's things like age gradients. There's things like multiplicity might be much higher towards the center of the galaxy. And we know multiplicity changes planet occurrence rates, that can suppress at some distances and maybe even enhance at others. And then there's the radiation environment in the center of the galaxy. This planet radius value that we see, we think one of the reasons we see it is because there's a size of planet which is not big enough to hold on to its atmosphere in the face of the stellar radiation, so it loses it and becomes a smaller planet. So maybe if you looked right towards the center of the galaxy, you wouldn't see any of these intermediate sized planets. You'd only see stripped cores or planets that ran away to be gas giants and got big enough that they could survive. Their mass was enough to hold on to their atmospheres. So there's a bunch of physical reasons why you might expect to see some change in occurrence rate as a function of distance to the center of the galaxy. But we're not really probing that with Kepler.
Yeah, and I think in a few years, hopefully Roman will observe the galactic center. It will observe hundreds of thousands of stars, hundreds of millions of stars there. And obviously it may detect many transit planets. Are there any studies?
Yeah, so the only one I know,
mind,
so Ben Monte had a paper in 2017 which predicted that Roman would find 100,000 transiting planets. That might be interesting statistically. I think, again, coming back to this Kepler problem, very unlikely that any of them will be interesting individually because they'll be so faint, and in particular because it's so crowded, it'll be hard for us to know which star. Every pixel will have multiple stars, so it'll be hard to know which star actually has the transit. But you'll be able to ask these bulk statistical questions like, we are looking at 1 million stars and we see 1,000 transits, therefore the population must look like this. So we can do these statistical tricks. And hopefully that gives us insight into what these properties of the planet population is. This prediction that Ben made, is based on what we know in our local galactic neighborhood. So if the prediction is wrong, that already gives us information about okay, so planet formation is harder or easier or changes in this way in center. So that's, yes, I'm excited about Roman helping us probe a bunch of this stuff.
Right, thank you. Another question is coming from Radek.
Yeah, so it's actually a comment. I wanted to comment about these transiting planets that Roman is going to find. So yes, there's a paper by Ben Montes, which gives the number of 100,000. The same number appeared in the one of the very early papers suggesting to do such a mission for microlensing, and it was, I think, paper by Bennett and Ree in 1996. Cool. So it was known much before. And one thing we know about these planets is that they'll be basically Jupiters, mostly hot Jupiters, just because of the noise floor of the Roman, which is significantly worse than in Kepler. We estimate it's an
instrument noise floor or like a crowding noise floor because of the stellar, all of the stars in the same pixel.
So both of these contribute, and in all simulations we assume 1 millimagnitude is a noise floor. So it's significantly worse than Kepler had, but of course Roman is going to observe huge number of stars.
Right. Yeah, I was actually curious because, Roman's a much bigger telescope than Kepler, but, is not designed, it's not, its main science isn't very, very, very ultra high precision photometry. So I was curious how much of the noise floor was because of choices made with the instrument as compared to choices made in the field. Like you're looking at the center of the galaxy, it's noisy.
Yes, I think the fact that it's near infrared detector, it's also contributing to higher noise floor.
That makes sense.
Great, any more questions? I have one in between. I was really much impressed by the artificial intelligence application when you combine Gaia and Lamos. And could you come back to this and tell us a little bit more? What I understood, you used Gaia and Lamos as a training, and then you kind of you train your system so that it comes up with the missing data, essentially missing astrophysical data, right?
Yeah. So for the training set, we have colors from, we have ground-based colors, we have Gaia DR2, and we have LaMost. So we use those to work out for a given color in Gaia DR2, what would you have gotten from LaMost? So that then we can go to the full training set and say, okay, now we only have Gaia and DR2, what do you predict? And of course, you have larger uncertainties because we even have larger uncertainties on the ones where we have LaMost, because the idea is to have a uniform set where we do it all the same way. We hands off, just pretend we don't have LaMost for anything and just do Gaia DR2 and the photometry. But the idea is to have a fully uniformly generated set of parameters so that we haven't got weird populations that are better known or offset from the others. So yes, this was Kevin Hardegree-Ullman came up with this, and it has worked very well. And now we're doing it for TESS. So TESS, the TESS input catalog is 1.8 billion sources because it's every point source on the sky down to 18th magnitude. So it was basically an assembly of a lot of catalogs of data, which is the exact thing we're trying to avoid. So he's working now on scaling this up for TESS. So TESS plus Gaia DR2 plus LaMost, and there's actually a bunch of other ground-based surveys, Galar, Apogee, Rave. So he's working right now on like a master training set so that we can get the whole TESS catalog on the same footing and start to ask these statistical questions with that too.
Awesome. And I guess this works best for, it scales with the magnitude, I'm sure, because the precision, both in Gaia and other surveys is depending on this. But also, I guess, well, you should look into the newest Gaia data release, the EDR3, which is significantly better than DR2 and is more complete, especially in the regions of where the crowding is an issue. And at least
I think he might. Now that you say that, I think for the TESS stuff, he might have gone to EDR3. I'm not 100% sure. One thing I will say, this works really well for temperature and log G. It doesn't work well for metallicity. The parallax and colors are just not very constraining for metallicity. That's where you really need the power of the high resolution spectrum to be able to resolve the lines. So we do have metallicities, but they're bonkers uncertain. Like it's, there's very little correlation between the real most metallicity and our predicted metallicity. So I don't want to give anybody a false sense of hope that we've somehow magically come up with photometric metallicities that work better than photometric metallicities ever have in the past. We have not.
Yes, you can do magic with artificial intelligence, but it's not there.
Yes, exactly.
Okay, great. Thank you, Jessie, for this. I don't see any more questions, so I'll do the thing on behalf of everyone. Thank you for joining us. Thank you all for joining us today, and we continue the topic of planets in the coming weeks. So see you next week, and thank you and goodbye.